the air conditioning off. It is getting very hot in here. This food is going off in this heat. I better get down to the cave and get that fridge working, or I'm going to lose it all. Well, have to wait. Need it on the science line. How can I help?
Stella, there's something we don't understand.
Yeah, we filled these two caps from the same bottle, right?
But they feel different. This metal one feels cold, and the polystyrene one feels warm.
If the water's the same, they should be as hot as each other, shouldn't they?
What do you think, Stella?
I'm on to it. I think first of all we need to find out what heat is all about. Not here. It's cooler in the cave. Energy can be released as heat. So when we say how hot something is, what we're really talking about is the amount of energy it has. Now, energy always flows from a hotter area to a cooler one. This metal bar is covered in a special material that changes colour when it gets hot. The energy is transferred from the water to the bottom of the bar so it gets hotter. And the changing colours show the energy transferring along the metal. But what is actually happening? Particles in a solid are vibrating all the time. How much depends on how hot they are. More energy means more vibration. The metal bar is heated at the bottom and the energy moves from one particle to the next, making each in turn vibrate faster. The energy always moves from hot areas to cooler ones. Once you know that energy always flows from hotter to cooler areas, you can find ways to control it. And this can be very useful indeed, as Femi's about to find out.
I'm late and I'm hot. But my investigation is with a man who couldn't just cool down by taking off a layer because the air around him was very, very cold.
This is a climbing wall where climbers train.
Now, where's Alan Hinks?
Hi, Femi. I'll be down in a tick.
Alan Hinks has just come back from climbing Nanga Parbat in Pakistan, over 8,000 metres high.
So what do you do when you're up a mountain and you get hot?
When you get hot, heat flows from your body to cooler areas.
OK, so it goes into your clothes and then into the air around you.
Yes, but I want to control the flow to prevent that. Well, I knew if I could store the heat produced when I was climbing, then I could use it to warm myself up once I stopped climbing and cool down.
But how could you do that?
I'll give you a clue. Try climbing in your fleece.
You want me to climb?
Phew, made it. Now to look at my fleece under a special camera that's sensitive to heat.
You can see it on my face. It's different colours depending on how warm various bits of my face are.
My eyes are hottest, my nose is cooler, and my green hair coolest of all. It's the same on your body. My fleece shows hot spots under my arms and up my back. If we could get heat to flow to the cooler areas, couldn't we store more?
That's right, and I've got a special fleece here, just like the one I took to Nanga Parbat with me. So, give this a try.
Thanks, Alan. This investigation's driving me up the wall.
Alan's climbing in an ordinary fleece so we can compare them. Right, let's see how the special fleece has got on. There is heat stored in more of the special fleece. Compare it to Alan's ordinary one. The special fabric allows the heat to flow more easily. This is how it would have spread as I got hot. And it stores the heat for longer. You can see it with my handprints. The ordinary fleece loses heat faster. The special fleece is better at spreading it and storing it.
I see. When I touch the metal cup, The heat was flowing out of my hand quickly, so it felt cold.
But the polystyrene one stops the heat from flowing so fast. As this stays in your hand for longer, it feels warmer. So the temperatures of the cups aren't different then, Stella?
That's right. They are at the same temperature, and you can check that with a thermometer.
Yeah, they're exactly the same. OK, Stella, but what is temperature?
Well, the temperature of something is the measure of how hot it is. Temperature is measured in degrees, and the scale we use mostly nowadays was worked out by a Swedish astronomer called Celsius. Now, a thermometer would be useful for me to check that the cave isn't too cold for my plants. But this one hasn't got a scale. Probably could make one. The bulb is surrounded by melting ice, and the ethanol has had time to settle down. It stopped moving. The ethanol is dyed blue so we can see it. Ice is frozen water. And this mark indicates the freezing point of water, which Celsius called 0 degrees. Heating the ice will turn it to water. The energy in the water is being transferred into the ethanol, so it raises its temperature. The heated ethanol moves up the tube because it's expanding. The water is now boiling, and the ethanol has stopped rising. This mark is the boiling point of water, which Celsius called 100 degrees. Now, by dividing the distance equally between the 2 points, we get a scale. And the level of the ethanol will tell us the temperature of whatever's surrounding it. So, if I leave this here, it will tell me the temperature of the cave. Not quite as accurate as the real thing, but not bad.
But look at this, Stella. What does temperature tell us here?
This container has 4 litres of water in it, and this one only 1 litre. We're heating them with the same sized flame.
And we've been heating them for exactly the same time, so they've both been given the same amount of energy.
But the water in the small container is at 50 degrees Celsius. And the big one is at 32.3 degrees Celsius. Why, Stella?
You can look at it this way. And this 20 pounds represents the amount of energy given to each container. So if I give it to the 4-litre container, it's like giving 4 people 20 pounds. Each gets 5 pounds. Now, if I give it to the 1-litre container, it's like giving 1 person 20 pounds. So they get the whole 20 pounds. So it's the same amount of money, but the more people there are, the more spread out it is. It's the same with energy. In a liquid, particles move like this. The large container has more particles than the small one, so energy from the flame is spread out more, like the money. This means that each particle in the large container gets less of the energy from the flame than the small one, so they'll move more slowly. When we measure temperature, what we're measuring is how fast the particles are moving. The slower they move, the lower the temperature. Now, if you want to keep anything at a steady temperature, you need not only control the energy going in, but what's coming out. Something I'm failing to do. I hope Femi's having more success.
Pretty flamingos. Outside here, it's a rather warm 25 degrees Celsius, but I'm about to go inside this building where with the air conditioning, it makes it 20 degrees Celsius. Now, 5 degrees doesn't make much difference to me, but I'm about to investigate some birds where just plus or minus 0.5 degrees Celsius is the difference between life and death. Steve Broomfield looks after birds in the earliest stages of life, when they're still in their eggs. Hi, Steve.
Hi, Femi.
Who's this then?
This is an African grey chick. He's a few days off hatching now. As you can see, this is the embryo. It's the dark material at the bottom, and we've got the airspace at the top. Should we put him in the incubator?
Yeah. Steve, what does this do?
Well, this is the incubator, and its job is to keep eggs such as this and this curassow egg at the right temperature until they hatch.
So what is the right temperature?
Well, that's between 36.8 and 37.8 degrees Celsius, and it must stay between those two values or the chicks could actually die.
Right, so that's really important. How do you make sure the temperature is actually kept constant?
Well, we can't actually keep it constant, and it's the role of the thermostat to switch the heaters on when it gets too cold and switch them off when it gets too hot.
I better put this chick back.
And I'll go and check the computer.
It's not kept constant. Let's try and work this out. When the heater's working, it warms up the air inside the incubator. When the temperature has risen to 37.8 degrees Celsius, the thermostat turns off the heater. The heat then flows to the cooler air outside and the temperature falls. At 36.8 degrees Celsius, more heat is needed, so the heater switches on again. So, Steve, rather than the incubator having to be kept at a constant temperature, it actually has to go up and down.
That's right, look. These are the temperatures over the last few hours.
And if it goes outside these limits, the computer sounds an alarm. Right, off to feed the curassows.
These are black curassows. They come from South America, where it's very hot and steamy in the jungles.
How do they manage with our British weather? Because it's obviously a lot warmer in South America.
That's right, it is. But you'll be surprised how well they adapt to our climate here.
Steve, what's that noise?
That's the incubation alarm. Come on.
The incubator's miles away. I don't remember running this far.
You check the computer, I'll look at the incubator.
The temperature was dangerously low.
Femi, look at this.
But Steve was onto it.
When you put the lid down, the thermostat was too near the egg.
The egg was cooler than the air around it, so heat had flowed into it from the air, making the air temporarily cooler. This is what the probe was measuring. Sorted.
Fancy some lunch?
Love some. As long as it's not omelette.
The fridge is working now. I just need to give it some time to lower the temperature in the cabinet. In the meantime, what's the temperature out here? 22 degrees Celsius. Oh, that's good. I can bring some plants out here. Getting temperatures right isn't just something you need to do with living things. Now, these two bars are made of two different metals, brass and iron. Now, if I heat them in the same flame, the brass expands more than the iron. So, if I fix them together and then heat them in the same flame, what do you think will happen? Both still expand, but by different amounts, and the force generated is big enough to bend the bars. And in some jobs, knowing this can be very important indeed.
I need this to stop me getting too hot in the sun. But how do you protect something that's 1.5 million kilometres nearer to the sun and is worth over £15 million? This investigation is in space.
Trevor Edwards designed satellites. We're in a clean room, hence the hats.
Trevor.
Hello, Femi.
Hello. Now, what are the problems of a satellite being in space? Because it is an unusual environment.
Yes, this is a model of a part of a satellite called SOHO. And it's in an orbit where one end is always facing the sun. The metal here can reach about...
The metal nearest the sun can get to 80 degrees Celsius, but the other end, which never gets heated, could be as low as -10 degrees Celsius. This means the metal would expand at different rates and cause the satellite to warp.
So, you want me to investigate how to solve this problem?
Yes, please, Femi.
I'm on the case. The moment, the one that
Simon Peskett also worked on SOHO. He's got an idea that might help. This equipment simulates the conditions in space. These aluminium rods the metal Soho's made of are connected to a mirror which reflects a laser beam onto a screen. That's where it is now. I heat one rod to 80 degrees Celsius, which will make it expand. And cool the other to -10 degrees, which makes it contract slightly. The different rates of expansion cause the mirror to twist and deflect the beam. AL for aluminium, but Simon has another metal to try. It's called Invar.
Wow, let's see what Invar can do.
We change the rods and repeat the process.
Now let's see what's happened to the beam. Excellent, it hasn't moved at all. Time to find Trevor to show him my discovery. Trevor, I think I cracked it. This is Invar, and it doesn't expand or contract at all.
Well, thanks, Femi. That will certainly get us over the problem of warping, but there's one drawback.
What's that?
Try weighing it.
Okay.
Aluminium, 160 grams. Invar, 420 grams.
I need to do some serious thinking.
Ah, this is the serious thinking I love. Phew, it's hot. I'll just cool down a bit. Little drink. Ooh, that ice is cold. Still, my hands will warm it. Hang on. Cooling, warming, got it.
Trevor, I've got it this time. Whoops. We need to cool the hot bit and warm the cool bit.
Well done, Femi. That's exactly what we did on Soho. This is a radiator. It allows the heat to flow from this part of the structure into space where it's much colder. And this tiny heater makes sure that this part of the structure is at the same temperature as the front, so therefore there's no distortion.
And the satellite camera can take wonderful pictures of the sun, and I can get on with doing some more serious thinking. Where did I leave my drink?
There, my fridge is working again. Now, have you ever noticed how hot it gets at the back of a fridge? And have you ever thought of where that energy comes from? Have a think about it. And here's another one for you. I put this piece of paper in this flame. It burns. But if I make the paper into a dish and put some water in it,
I think it's because the water's making the paper wet, so it won't burn. But it's not soaking through. I'd see drops at the bottom.
When you heated the paper on its own, it got hot enough to burn.
Yeah, right, so the water paper down. But that's the wrong way to look at it. Heat flows from hot to cold.
Yeah, so they heat the paper into the cooler water.
And that stops the paper reaching the temperature it needs.